Welcome to Uni. What? Today you will complete the chapter Light, Reflection and Refraction. Let's begin. Mirror formula, a formula that indicates the relationship between the image distance, object distance, and focal length of a mirror is known as the mirror formula. If the image distance of a mirror be represented by u and the focal length by f, then mirror formula can be represented as 1/u 1/v equals 1/f, where v equals distance of the image from the mirror, and u equals object distance from the mirror. Also f equals focal length of the mirror, and r equals distance between center of curvature and pole. Therefore, f equals r/2. Linear magnification of a mirror. Linear magnification of a mirror is the ratio of the height of the image to the total height of the object. Thus, linear magnification is height of image/height of object. If h1 be the height of the object placed in front of a mirror, and if h2 be the image formed, then linear magnification m produced by the mirror can be represented as m equals h1/h2. However, linear magnification of a mirror is also equal to the ratio between image distance and object distance from a mirror, but with a negative sign is represented as m equals v/u, where v equals image distance and u equals object distance of a mirror. If the magnification has a positive plus sign, then the image formed will be virtual and erect, and if it has a negative minus sign, the image formed will be real and inverted. Lens. A lens is a piece of transparent glass bounded by two spherical surfaces. It is of two main types. 1. Concave lens. A lens having both of its surfaces curved inwards is called a concave lens. It is thin in the middle and thicker at the edges. It is also called a diverging lens as it diverges a parallel beam of light rays incident on it. 2. Convex lens. A lens having both of its surfaces bulged outwards is called a convex lens. It is thicker in the middle and thin at the edges as shown under. It is also called a converging lens as it converges a parallel beam of light rays. Terms associated with lenses. The various terms associated with the lenses, concave and convex, are 1. Optical center. The central point of a lens, concave or convex, is called its optical center. It is represented by the letter C and has the property that it allows a light ray to pass through it without any deviation. 2. Principal axis. The principal axis of a lens is a line that passes through the optical center of the lens and is perpendicular to both of its faces. 3. Principal focus. A. Concave lens. The principal focus of a concave lens is a point on its principal axis from which light rays, originally parallel to the axis, appear to diverge after passing through the lens, has a virtual focus represented by the letter F. B. Convex lens. The principal focus of a convex lens is a point on its principal axis to which light rays originally parallel to the principal axis converge after passing through it. A convex lens has a real focus represented by the letter F. Sign convention for lenses. The various sign conventions used for measuring distances in the ray diagram of lenses are: all distances are measured from the optical center of a lens. The distances measured in the same direction as that of incident light are taken as positive. The distances measured against the direction of the incident light are taken as negative. The distances measured upwards and perpendicular to the principal axis is considered positive. The distance measured downwards and perpendicular to the principal axis is considered negative. Rules for images formed by a convex lens. The various rules employed for obtaining images on a convex lens are: an incident ray of light passing through the optical center of a convex lens emerges undeviated after refraction through the lens. An incident ray of light parallel to the principal axis of a convex lens passes through the focus after refraction. An incident ray of light passing through the focus of a convex lens becomes parallel to the principal axis after refraction. Formation of images on a convex lens. Object at infinity. When an object is at infinity from a convex lens, the image formed lies at the focus, which is real, inverted, and highly smaller in size than the size of the object. An object placed beyond 2f. When an object is placed beyond 2f in front of a convex lens, the image is formed between f and 2f on the other side of the lens, which is real, inverted, and diminished, i.e., smaller in size than the size of the object. Object placed at 2f. When an object is placed at 2f in front of a convex lens, The image is formed at 2f on the other side of the lens, which is real, inverted, and of the same size as the object. An object placed between f and 2f. When an object is placed between the focus and 2f in front of a convex lens, the image formed lies beyond 2f. The image formed is real, inverted, and larger in size than the object. An object placed at the focus. When an object is placed at the focus of a convex lens, the image is formed at infinity, which is real, inverted, and highly enlarged, i.e., larger in size than the object. An object placed between C and F. When an object is placed between the optical center and the focus of a convex lens, the image formed lies behind the object on the same side. The image formed is virtual, erect, and magnified, i.e., larger in size than the size of the object. Rules for image formation by a concave lens. An incident ray parallel to the principal axis of the concave lens appears to be coming from its focus after refraction through the lens. An incident ray passing through the optical center of a concave lens goes straight without any deviation from its straight path. Image formation by a concave lens. Formation of images on a concave lens does not depend upon the position of the object in front of a concave lens. A concave lens always forms a virtual, erect, and diminished image, i.e., smaller in size than the size of the object. Power of lens. The power of a lens may be defined as the reciprocal of its focal length expressed in meters. It is represented by the letter P. Thus, power of lens equals 1/focal length in meters, or P equals 1/f, where P equals power of lens, and F equals focal length of the lens. The SI unit of power of a lens is diopter, which is denoted by the letter D. The power of a lens is said to be 1 diopter if its focal length is equal to 1 meter. If F is given in centimeters, then P equals 100/f. However, a convex lens has a positive focal length and a concave lens has a negative focal length. Thus, a convex lens has a positive power and a concave lens has a negative power. Lens formula. The formula which gives a relationship between the image distance, object distance, and the focal length of a lens is referred to as the lens formula. If U is the object distance and V is the image distance and F is the focal length of a lens, then the lens formula can be given as 1/image distance 1/object distance equals 1/focal length, or 1/V 1/U equals 1/f. Linear magnification of a lens. It is defined as the ratio between the height of an image to the height of the object. If h2 be the height of the object, and if h1 be the height of the image, then the magnification m of a lens can be given as magnification height of image / height of object, or m equals h2/h1, where h2 equals height of image and h1 equals height of the object. However, the ratio of image distance to object distance is also known as magnification. If U be the distance of the object and V is the distance of the image from a lens, the n magnification m of a lens can be given as magnification equals image distance / height of object, or m equals V/U, where V equals image distance and U equals object distance. However, if m has a positive sign, then the image formed is virtual and erect, and if it has a negative sign, then the image formed will be real and inverted. So what have you learned here? Light seems to travel in straight lines. Mirrors and lenses form images of objects. Images can be either real or virtual, depending on the position of the object. The reflecting surfaces of all types obey the laws of reflection. The refracting surfaces obey the laws of refraction. New Cartesian sign conventions are followed for spherical mirrors and lenses. The mirror formula gives the relationship between the object distance, U, image distance, V, and focal length, F, of a spherical mirror. The focal length of a spherical mirror is equal to half its radius of curvature. The magnification produced by a spherical mirror is the ratio of the height of the image to the height of the object. A light ray traveling obliquely from a denser medium to a rarer medium bends away from the normal. A light ray bends towards the normal when it travels obliquely from a rarer to a denser medium. Light travels in a vacuum with an enormous speed of 3x 108 ms1. The speed of light is different in different media. The refractive index of a transparent medium is the ratio of the speed of light in a vacuum to that in the medium. The lens formula gives the relationship between the object distance, U, image distance, V, and the focal length, F, of a spherical lens. The power of a lens is the reciprocal of its focal length. The C unit of power of a lens is diopter. Thank you and please subscribe. See you.